Hey, I wanted to get a really dumb idea out of my head, and now it's 1:30 a.m. and I don't want to try to pick this up another day, so I'm just going to record this real quick and release it onto the internet. I just wanted to make a little multi-processing server that would support the network and spread jobs across multiple computers. Kind of a CPU only workload little demonstrator. So let's start with a dumb example, which is just going to be the example of a computer doing work. So I picked the sieve of Eratosthenes. Eratosthenes was a guy who figured out a method to find prime numbers, and it's not really important, but it's just going to count a lot. It's really not a very efficient algorithm, but we're going to run this, and I'm going to put a little timer in there to make it run a little bit slower, so it's a little bit more, doesn't take 0.0 seconds to complete. And without making you watch the timers go by, when you run this, it checks every number. It takes about 5 seconds to find the first 1,000, or all the prime numbers under 1,000. Ta-da! Okay, so that's just a computer doing work, but we're counting to 1,000. It would be kind of handy if you could split that up, right? So right now it's doing both the generation of inputs, which is the numbers 1 to 1,000. Check these for being primes. And it's also doing the execution, which is the part where you say, okay, is 600 prime? And it basically checks if it's a multiple of anything below that, and then marks it as prime or not for its final output. So that took 5 seconds, and one computer is doing both. Now, what if we split it so that the generation of inputs was one task and a worker did the actual computation as a separate task? So the reason you would do that is so that you can have one generator. So instead of having 1 to 100 or 1 to 1,000, you have like 1 to 100 and 101 to 200. And that's basically the premise behind multiprocessing, right? You split the job up and you run multiple of it. But the trick that would make this really handy is not multiprocessing, because splitting across cores, you can also do that with threads, but you can't really split your computing across more CPUs than are in your computer. So let's move it to the network by adding a little WebSocket server. So what the WebSocket server is going to do is it's going to basically listen. Generators are going to connect to it and say, hey, I have this batch of jobs I want to get completed. Clients are going to show up and say, I have this many cores, keep me busy. So that's what we're going to do next, is basically use the little WebSocket server and take these batches, whatever the inputs are, however many cores it's going to take to do that batch, and it's going to send those to the server. Server will split them up to clients, and then when clients return results, the server is going to give it back. So, right. Oh, I was supposed to show this thing too. The only thing I did for the worker function, this is like the exact same sieve functionality, but it accepts the start and end point as input on the command line. So now I can run this for a range, which is, from, instead of just always 1 to 1,000, I can give it the numbers 201 and 300, and it will do that sub-range, which is all I needed to make it into a worker. So the worker takes the same exact amount of time if it does the same exact range. But now we're going to run a server, and this server has already got some stuff in the logs, but it should still run exactly the same. And I also have a little monitor that I wrote here. So this is the state of it right now, which would be something like workers. You've got an ID of 2, you've got an ID of 3, because the old one's disconnected and these ones got new IDs. So here is a worker with 4 cores and a worker with 4 cores. and anybody that can connect to this IP address would be able to push and pull inputs and results. So now I'm going to time the generator client, which is going to generate 1 through 1,000 in blocks of 100 and send them off for work. So when it does that, it's got the 10 jobs. They start coming back pretty quickly. And if I scroll up a bit, in Tmux, you gotta hit the key first. What this will originally do is it will get that batch of 10 jobs all at once from the client, and it will have 4 jobs assigned to each worker. And then as those jobs start finishing, we should see jobs waiting 1 and jobs waiting 0, because as the workers finished one job, they got another one right away. And then towards the bottom, a lot of events here. Should say something like cores used 1, jobs assigned 1, jobs waiting 0. So this worker is not being used to full capacity because the job queue has already been emptied out. But, you know, it's never that easy to just hit buttons and get things to come out. I think what I have here is, what is this? It's a 0, minus 1, 2, 3, 4, 5, 6, 7, 8. It's like it's still waiting for 2. That doesn't seem right, because, well, there's the last one. Yeah, let me just start these guys all over again. So I'll start the server, start each worker, start the monitor, and I'll start the generator. Okay, and of course you should assume that if you break something into 10 parts and do them 4 or 5 at a time, that it'll be much faster. But yeah, that's kind of the basic proof of concept there. I think there's like async bugs in this, and it's not especially robust, but I just think it would be super fun to put something like this on the internet and sling a bunch of different jobs around. Oh, and the name. So this whole idea comes from goofing around on the Tenebrous Tales Discord, and Tenebrous means like grim or spooky, so I was trying to find a synonym for that that's alliterates with C. So CrepuscularCluster is what I called it, and it'll be on GitHub in a minute, and then I'm gonna go to sleep. Bye.